So what is a TPM? You can kind of see over here, we have different versions of TPMs. Obviously it's some sort of IC, but we can have it as an expansion. We could buy stuff like that. So a TPM, Trusted Platform Module, it's a dedicated crypto decelerator. So it actually doesn't speed things up. It doesn't run very fast. It's actually really slow, and we'll kind of talk about that in a bit. The things that it does really has two primary features. And I would say the biggest use case of the TPM is to prevent like spoof-based attacks, where somebody says that they are your hardware, but they really aren't. So it's very nice. The other thing that you're able to do, you're able to generate and store keys in the TPM. It'll never give them out. It'll never ever let you have them. So the TPM is very secure. The problem here though, so it not only does, it stores keys, but it also measures the system integrity during boot. So as your computer boots up, it goes through this basically chain of trust. It starts off with the most trusted module, which starts and it loads the bootloader, or the BIOS, and then that loads the bootloader. So you go and you pass control from module to module. Well, what happens, what the TPM does is as you pass control, well, before you pass control, you actually send a hash of the status of the module that you're talking about to the TPM. And the TPM has been configured with these things called basically golden measurements. Essentially things put in by like the IT department or possibly the manufacturer like Dell or something. And they'll put in these golden measurements that say when I boot up, this is what it should look like, right? So if you have a laptop, it comes with a pre-installed hard drive, it comes with pre-installed this, that, right? As it boots up, it's checking to make sure that those really are what's on the system, and it has some sort of golden measurement that it can check against. So again, that's measured boot. It doesn't stop the boot up from happening. If it sees that something's gone awry, it doesn't stop it. It just lets the system know later. So kind of a difference there between secure boot and measured boot. It provides attestation that the machine is in a trusted state. So essentially, it has these registers. The machine can, if the registers are configured in a certain way, it'll release secrets. And the way that they are configured is by the system state. So it's by the status of the machine. It's not actually something that we provide. It's just a state that the computer has that will unlock certain secrets of the TPM. Yeah, last thing here, it's a standard, so it's defined by the Trusted Computing Group. You may be like thinking in your head, why did Windows require this device and why is it made by this one company? But it's actually not just made by this one company. That's who defines the standard, but it's sold by many different companies, many different manufacturers. Okay, so there's different types of TPM. So first one we have, you may be asking like what is a TPM? It can have three different forms typically. So this first one here as an IC, that's a discrete TPM, and that's essentially just an external chip that you buy. It's a TPM usually made by somebody like Infineon, is the most common manufacturer. And it has the highest physical isolation. So people argue in both directions. They say, hey, is it better to have the highest physical isolation, be as far away from the processor as possible, or is it better to have maybe the highest internal, it's inside the processor, it's very hard to tamper with. So people kind of debate whether it's better to have it as external or an internal chip. So the internal kind would be the firmware TPM. Essentially you'd have like an SoC, something like the Ryzen 1000 series chip. They inside would have a small TPM, a little architecture that basically emulated TPM, and it would be managed by this kind of chip environment. So some people say that that adds more security, some people say it adds less. We'll kind of show what it actually does. Then the third thing, virtual TPM. Obviously, if you have something like VirtualBox, you're going to pull up a menu like this and you can add a TPM. So if you ever need to add a TPM, you can emulate it as well. Just know that if you emulate it, it's going to be storing your stuff on disk and not actually in real TPM. Okay, so who makes TPMs? Why do I need it? Well, the number one manufacturer of TPMs is probably Infineon. But behind them, it's Novaton, STM Microelectronics, and then Intel and AMD both have their own FTPMs, firmware TPMs. Intel's is called the PTT, and AMD is called the FTPM. Again, why do you need it? Well, like I talked about, Microsoft requires it for TPM 2.0, or for Windows 11. They require TPM 2.0, and for Windows 10, they require TPM 1.2 or less for the BitLocker keys. And you can also have, TPM 2.0 for that. Yeah. So that's kind of why you need it. Most people use Windows. I mean, at least Enterprise does. But yeah, I mean, is it to be actually trusted? So the name trusted here is not actually saying that this thing is some like hardware silver bullet, hardware security silver bullet. It actually is implying that we as the users are placing our trust in this chip and we trust it to do its job. Doesn't mean that it's actually to be trusted. In fact, it can have some severe hiccups, as we'll see shortly. But I guess we place our trust in it. It's a hardware root of trust. It stores keys, and we kind of trust it to do its job. We have to use other things to make sure that the TPM is trustable, I guess. And so the interesting thing is this talks on TPM, but there's many different layers of security that a computer has to make sure that the TPM is working, but also other things are working as well, so that the TPM can't just overload. Yeah, that's kind of what the TPM actually is. Again, it's not actually trusted. We place our trust in it, and that's why we call it trusted. So what does it do? Well, it stores secure keys. It can generate keys, RSA keys, 1024, 2048-bit. You can't get the keys out of it once you ask it to make a key. So what you can do is you can ask it to make a private-public key pair. It'll give you a public key, and it'll store a private key inside of it. Basically, the key itself is two separate things. You use your public key to say, I am this, it's kind of your ID badge, and your private key never actually comes out. It's just kind of maybe like a barcode on your ID badge. Occasionally you'll flip around and scan when somebody wants to check and make sure it's you. So, right, we have these keys that we can store, they don't come out, and we also have these things called the PCRs, or Platform Configuration Registers. So essentially, they store cryptographic hashes of the state of the BIOS, UEFI, bootloader, kernel, drivers. It does this interesting algorithm to kind of ensure, with a high degree of likelihood, that your system has not been tampered with. And we'll go over that shortly, just one more slide to get through. So it can also do sealing. It can encrypt a secret such that it will only decrypt it if the PCR values don't matter, they match a specific boot state. So that's pretty nice. Why is that nice? We will decrypt if the computer is in a state that we like. I don't know. That's a good thing. We can use that for our advantage. If somebody tampers with the bootloader, the PCR changes, the secret's sealed. So if somebody messes with stuff, the PCR is changed, and it kind of keeps our system secure. Again, the TPM can sign PCR values, so a remote system can validate that we are who we say we are. And then as far as being a decelerator, I kind of talked about that earlier, but to actually get into it, there's kind of two main reasons here. One, the TPM itself is kind of designed to prevent spoofing attacks, but they make it intentionally slow to kind of prevent anti-hammering attacks. And so a hammering attack is essentially like just brute forcing, right? It's kind of in the name. So it's implying you're brute force just trying to, attempt password after password. You guys have probably experienced this where if you get a password wrong like 3 or 4 or 5 times, something happens that says, hey, you can't log in anymore, even if you get your password right. Usually that's like some anti-hammering thing to stop brute force attacks. But yeah, that's kind of why it's slow. Helps stop brute force attacks. Your computer's operating at gigahertz, and this thing operates at 100 megahertz usually. They're energy friendly, and so that's another reason. This chip is like an add-on. How do you sell? Imagine if the TPM took up the same amount of power as a processor. People would not be happy because if TPMs were required, they basically need to have the power for 2 processors. So they want to make this add-on like as lightweight as possible. They make it low power, and so it has a very low power internal clock, about 100 megahertz. Okay. Cool, so these TPM things, they exist and they're in pretty much every computer nowadays, but if we never used it, how has it actually been protecting us? And so we have 2 different kinds of boot security here. When your computer boots up, there's kind of some checks that need to happen. First, we have secure boot, so that's kind of enforcement. Secure boot's pretty powerful. It has the power as it's booting up to stop the boot process and say, you know what, I'm done. this is an issue and kind of point out some error. The TPM does not have the ability to stop the boot process, and so it's a measured boot. It's a little bit different. It's enforcement versus evidence. And if you look at secure boot, it verifies the digital signatures during boot. It only allows firmware, bootloader, kernel signed by trusted keys, and it stops boot if verification fails. So it's enforcement. It says, hey, is this policy being met? If not, I'm going to take action. Whereas measured boot, that the TPM does, each boot stage hashes the next stage. It's this chain of hash, and at the very end, you check against the golden hash stored by IT admin, manufacturer, and you say, hey, is this correct? If it's correct, your computer will boot up. I don't know if any of you guys have ever replaced a hard drive in your computer. I have. The SSD, when you pull, maybe you pull out your hard drive, you want to replace it with a solid state drive. You plug in the solid state drive, you're like, cool, turn on your computer, and the first thing that pops up is like blue BitLocker recovery key screen. And that's because you actually changed your hardware. And so now you have to go log in your account, get your BitLocker key, unlock it, and now you can set up this new drive. And so it's essentially securing, making sure that we can't just tamper with hardware, throw in some random phony drive and get it to boot up something we don't want it to. Kind of enforcing security in this machine. Again, as boot occurs, it hashes repeatedly, so it stores its current measurement in the TPM, who hashes this measurement. It passes control to the next module, rinse and repeat, and at the end, it makes sure it says, hey, is this hash that we've got, this chain hash, is this good against the golden measurement? And so kind of have it approved. Again, the golden measurements are stored and saved during something called the provisioning process of the manufacturer or IT department does. Okay, so here's kind of a graphic of what's actually happening here. So we have the core root of trust module. So this is like the most trusted thing that we have on the system. We trust every time that it's going to do its job, which is go to the BIOS and start things up. So before this thing can pass control to the BIOS, so first it's going to measure the BIOS, then it's going to store its own measurement, and then it's going to jump to the BIOS. If we fail here, it's not the TPM that's going to stop us. It's actual secure boot that's going to stop us, and that's other things taking place in software, in hardware, besides the TPM. So this more so is not secure boot, this is measured boot, where we're going to pass control, store our measurement, the next thing does the same thing, stores its measurement, goes on, stores its measurement, and eventually we get to the OS actually booting. Again, the whole time we're repeatedly hashing, so the PCR value is just one big value that we keep encrypting. So let's talk about now how these things have failed. So yeah, they got issues. Again, there's no silver bullet. Infineon made some chips, some TPM chips, and a big issue was that they all had this faulty prime number generator. Like the structure of the RSA prime numbers that they generated was predictable, and people could essentially take only public keys and then crack what the private key was. And so they could decrypt what private key pairs were using only the public key, which is really not good. You really don't ever want that. And yeah, I think only the knowledge, here it says only the knowledge of a public key is necessary. I believe it was only knowledge of one public key was necessary. It was so bad. And so it really had this big error, which caused many things, including identity documents, TPM, secure browsing, and they actually found that they put an asterisk here because that one was actually the least exposed out of all of them. But I think, yeah, the programmable smart cards were highly affected by this. Yeah, millions of devices were affected, BitLocker keys were left vulnerable. So never a good thing when all of our data gets exposed at once, especially when it's due to some hardware that you're supposed to trust. We bought this Infineon product because we want to trust it. Unfortunately, they engineered it wrong, and so it caused a huge issue for us. Another place where TPMs can fail, so again, we talked about these DTPMs. They're not great in terms of security. So it's kind of funny because it's a TPM, it's made to be this trusted platform module. But of course, it's going to be communicating through a copy trace, like always. I mean, you're never going to get around that. And so essentially, you can just bus snip this thing. Like in the picture, you solder some wires up to the data pins, and then you have an oscilloscope or logic analyzer that then just reads what the data being transmitted is. It can be useful for many different reasons. Again, the TPM never gives out the keys, so it can't really ever get the keys, but it can get information about the state of the TPM, which it can then use. So not great. We don't really want that. We don't want attackers to be able to probe the bus, but it's something that we have to live with these TPMs, especially if we have external ones. Again, they soldered wires on, used a logic analyzer, and they found that the volume master key was transmitted in plain text between CPU and TPM. So volume master key is not a TPM secret, but I guess for some reason it was being passed back and forth between the CPU and TPM, and that's not really good.
Right. What are like other things that are like snooped off the bus? Can people tell if a private key was just generated or a new public key was set without like knowing what that is if it's encrypted? Like what are the levels?
Yeah. They can get chip-specific information about the chip that's communicating with the TPM. They can get chip-specific information about the TPM itself. They can obviously snatch like public keys right as they come out because it's going to be transmitted to the CPU. So yeah, there's a few concerns here. I do know that not only, so there's concerns of what sort of information is coming out of these. The main reason why we kind of, I guess the reason why we like these is because they keep their secrets internal unless like this state is met. And so with these SPI bus sniffing attacks, they actually had to do some like really tricky stuff to get it to work. So one thing that they had to do was they had to take, and I'll show you, they talk about it in the AMD version, but they had to take a microcontroller with a power strip and essentially power this thing on and off so that the PCRs wouldn't freeze up and become a bad value. And so, like, to get the TPM to even work, they had to do a very finicky trick with the power just to sniff it. And so you'd have to have physical access to the device, which for one, if you have physical access, I don't know, you could ask the TPM to sign things anyways, especially if it was in a known state. So you could install some software. Again, this isn't really what the TPM is protecting against. It's more protecting for enterprise. Let's say that your enterprise has some OS. I'm the boss. I want all you guys to run my software. My software is going to manage you guys 24/7. It's going to tell me how many clicks per second that you guys do, so I can come in, I can yell at you. So I want to make sure that that OS is booted up every single time that I come into the, every single time you guys turn on a computer in the office. The way I enforce that is I essentially have, my golden measurement of what, if the chain of boot really booted up what I wanted, it would have some golden measurement, and your TPM would go through and it would hash everything, boot up, and check that final measurement and say, yep, they really did boot up your really terrible management OS, and it's like, yeah, so I don't know, the TPM makes sure that things happen for enterprise, and it can also store keys. People use it in very interesting ways. So here's kind of moving to more what you're talking about. They have, now the firmware TPMs are also vulnerable, and the reason why is because, originally firmware TPMs avoided the specific bus sniffing weakness because the TPM's completely inside the chip. So that's cool. Like, people can't just go accessing our TPM without deleting a chip. AMD, unfortunately, was having this thing called the secure processor, which was talking with the TPM. And that thing was sending information back and forth to the BIOS, I believe. And so they were able to bus sniff the BIOS line, and kind of the same result. And so they didn't really get away from it. They still were transmitting information on and off the chip. Not great. Again, these TPM things, they're very vulnerable to bus sniffing, stuff like that. But again, they never release their keys, so you'll never get a private key out of the TPM. You actually have to go in and open it, pry it open and look for a private key. There's kind of a visual of the attack again. For this same thing, they had a microcontroller with a power strip that would essentially like flicker power. Then they had a logic analyzer and SPI programmer, and that would read the information that the TPM was transmitting from this to the secure processor, that the secure processor was then transmitting to BIOS, and they could essentially grab that information and find out what was going on. So pretty interesting. Now to some more like just general talk. People think TPMs are because Microsoft wants total control. They think it's because the TPMs are spying on us, they're storing our data, they're sending it out. Well, the TPMs don't have any wireless capabilities inside of them. They don't really do anything uber interesting. They're kind of a weak hardware solution in terms of physical attacks. So yeah, I mean, it's not doing really any of those things, but what it really is doing is it can help enforce secure boot by doing measured boot. It can make sure that BitLocker is enforced, and again, does credential protection. It does not inherently spy or report data to anybody. But you can make them if you want. But so why are the TPMs good? So again, number one, hardware root trust. Prevents offline disk decryption attacks. Prevents, basically you can say that I am who I am, and if I'm not this person, you can't do something to me. And so it, kind of protects you. Again, measured boot lets enterprise verify device integrity. Secure key storage, you can store private keys in there and they won't come out. And then again, protection against credential theft. So I kind of have a quick demo. I can do it. I've done it 2 times now, and so I actually have been filling up space on the TPM because of how many keys I've been storing in it. So it did tell me on my desktop at home that my TPM was full and I couldn't add any more keys, but we'll see if it works. Okay, so how do SSH keys work? Well, okay, let's go back. Let's rewind. Let's secure the SSH keys using the TPM. So now that we know we have this TPM, how do we actually use it to do something good? How do we maybe store some secure information that we have? If anybody's used GitHub, if you ever want to pull from GitHub, use HTTPS. Sometimes there's weird things that happen with your specific hardware. It can't pull certain files because it can't grab them. I'm not sure why, but if you have an SSH key, it pretty much works flawlessly. So SSH is really nice. If you guys haven't set up an SSH key, doesn't do it. I think if you've set up CARP tools, you've done it. But how do they work? So now kind of talking about them. SSH key, like we said, is a public-private key pair, and it's used for authentication instead of passwords. So you have the private key, which stays on your machine. Where do you think it stays? TPM. No, what? Doesn't stay in the TPM. Typically, no. Where do you guys think the private key is when you make a private key public key pair? Well, where do you think the public key is on your computer? Where is it located physically? Ports. Well, the public key, you can see it in a folder. So it's just on disk. It's on disk. The private key is also right next to it on disk. It's another file. I could show you right now, but if I do SSH-keygen, it'll literally generate like 2 files, my private key and my public key. So if you guys want, you can just come up, stick a thumb drive in, copy my private key, then you guys get access like my OS, GitHub or something. I don't know. But not that it would help you that much, I'm saying. But the authentication works by proving that you own the private key without actually sending it. So essentially, number one, the client connects to the server then checks if your public key is in authorized keys. The server sends a random challenge, and then the client signs that challenge with the private key. So essentially, like, think about it, somebody sends a document, they're like, hey, I need you to sign this. You go, okay, pass it. That's what we're doing with this private key here. So the server verifies signature using your public key if it's valid on your key. So that's cool. It's using both keys, but the public key is kind of being used on all ends. Like everybody knows the public key, like it's public, but the private key itself is only on your machine. So again, I say SSH keygen, cool. Where is it? Well, the other funny thing too is everybody's SSH keygen defaults to a specific location, and most people just end up choosing that location. So if I want all your private keys, if your computers were open, I could probably just go to that location and copy them because you guys probably put it in the default location. But, okay, if you did like I did, you put in the default location, no password for it, then it would be saved, the private key would be saved here, and it's called ID ED25519, and it doesn't have a file extension. It's just a raw RSA. This ID ED25519.pub, what do you guys think that is?
Public key.
The public key. So this one's the private key, no file extension, this one's the public key. Big security risk, it's obviously stored locally, so anybody can grab it. That's not great, so how do we secure that? Well, we can use the TPM to generate keys. When a key is generated inside a TPM, it never exists as a file, it never leaves the TPM, root cannot read it, and the disk doesn't have it. So, kind of cool. And the TPM performs signing internally, so the challenge goes to the TPM, and the TPM provides a signature. It doesn't actually give out your key and say, yeah, here's the key. Is it the right thing? It just says, hey, I'm signing this. So, kind of nice to keep everything internal. You want to make sure you have permissions to actually do this. So if you run these commands and you don't run this first, you will have to sudo every time you want to talk to your TPM. So you run these so you don't have to run sudo every time, and then you install the TPM tools. Again, most of you probably have OpenSSH client, but some of these other ones you'll need. Check and make sure that the libtpm2 is in the correct location. So the shared object, make sure it's in user lib x86-64 links GNU, that thing. If it's there, everything's all good, then you can do this. So you can say TPM ptool init. So it's going to initialize some spot in the TPM. It's essentially going to say, hey, TPM, turn on and make a spot. And then you say TPM add token. You add the token, and it says, hey, TPM, add this token in the spot. And if you look, we didn't really do anything cool to the token. It just has a PID, has a label, it's got a pin, it's got a couple pins, so, I mean, okay, yeah, kind of cool, but it doesn't actually have anything in it yet, so we just made a token that the TPM can have. We list the token to make sure it's there, and then we want to generate the actual RSA key. So now we want to generate the key pair. We would go TPM ptool add key, and I label TPM, I give it a pin, 1234, the algorithm's RSA2048, and I call it the key label GitHub. And again, the private key is generated inside the TPM. So you can show that the TPM key exists by doing this now, TPM2 ptool list objects, it'll show that it exists. So, okay, at this point, you haven't generated the key pair. You've only generated a private key, RSA key, inside the TPM. Now you want to make a public key, so you'll do SSH keygen -d, and that's going to use the shared object to actually make sure that it's a public key pair for your TPM. Again, you read the contents. I don't care if you guys copy this. This is my public key, but the TPM has my private key, so I can't even get it off at this point. We're going to copy that hash, go to settings, go to SSH and GPG keys. Then we're going to click new SSH. And then we're going to add a new SSH key.
Your name was TPM key.
So yeah, we're going to have a new SSH key, paste that in, click add SSH key, done. And then you're going to want to make sure that your SSH agent exists. You're going to do eval SSH agent -s, add the TPM2 library shared object to SSH agent so it can use PKCS11. That's how it's going to use the TPM. So you want to add this. When you run this, it's going to say card added, and it's going to show that it added this library. And then you can do this. So SSH-add-L, that'll print out your public key if it all works. So that's cool. Then you can do git global username, git global user email if you haven't already. Then SSH to GitHub. You can pull stuff from GitHub. And the cool thing is now your key is stored in the TPM. Your private key isn't actually on your system at all. And so it's completely hidden from you. Nobody can steal it. Yeah. They can only, if they had control of your computer, they could get people to sign it. But think about that. Now, if I want to pull something from GitHub, maybe, I want to get into Rudy's stuff because he has some like 133 work I want to copy. So I'm going to go copy the 133 work from a private GitHub. It doesn't work because I don't have SSH rights. But if I was able to put malware on Rudy's machine, I could log in as him, and then I could SSH and download it to his computer, authenticating it with his TPM. That's cool. Problem is, at that point, I need like control of his whole computer to even like utilize the TPM. So that's kind of why the TPM is nice. I actually need full physical control of your computer to use it in the same way that you can use it to sign things. So it's kind of not worth doing that. So that's why a lot of attackers don't bother with the TPM. Yeah, that's my demo. I have it hooked up, and I show that I get cloned by my Puff Lab. So I made it a private before I did this. Yeah, any questions on that? Anything? Anybody? Anybody gonna go do this? No.
Now, where did you learn about TPM? This is like the first time I'm hearing about it.
I heard about it the first time was again with like that PC that my cousin gave me. But yeah, I've heard about them kind of again and again and again, especially in like embedded Linux. I've heard of them used to secure devices, and so I just really wanted to look into them and kind of see what they were. But yeah, any other questions? Anything else? If you guys do this, if you guys ever follow along with this, just know that you have to add a command that basically you have to enter your password for the TPM that you put the pin anytime you want SSH. So you just make sure that you have this command, some alias in your vim or bash rc, and then you can call that, and then you log in your SSH, and then you say I'm in the SSH and SSH stuff. So if you follow along with this and you don't listen to what I just said, and you turn off your computer and you turn it back on, and you go to SSH, it won't work. You'll probably have to like ask ChatGPT how to figure it out like I did. So, anyways, all right, thank you guys.